Welcome to this video on the simple regression model. Where are we in the course? This is part one of this course, Introduction and Basics of Regression Analysis. And I'm covering here the same material as chapter 2 of Wooldridge's book, Introductory Econometrics. And of course, I'm adding my own interpretation and take on it. Let me motivate what will follow by this screenshot from the New Yorker. It's basically saying that it's a no-brainer that college education is a good thing. It's just making life better, and therefore essentially suggests that everybody should attain some college education. And of course, ultimately it's an empirical question what the effect of college education actually is on productivity, satisfaction with life, wages, and so on and so forth. With that in mind, let us have a look at the workhorse model in econometrics, the simple regression model, and think about this empirical problem in the back of our minds, which is to relate wages to the level of education people have attained. These are the steps or the parts of this presentation here. So I'm going to first define the simple regression model, then I'm going to derive the OLS or ordinary least squares estimator, then I'm going to talk about properties of ordinary least squares on any sample of data, then I'm going to talk about units of measurement and functional form, and the last 2 points are expected values and variances of the OLS estimators. What is that actually? How can an estimator have an expected value and variance? We're going to talk about that. And the final topic is regression through the origin. Now, let's start with the definition of the simple regression model. So we're going to have two variables, y and x. Here's my y. Here's my x, that represents some population. Okay, and we're going to see what that means. But there's a y and there's an x, and what we want to do is we want to explain how y varies with changes in x. And I want to pause for a few seconds here and underline that word explain, because explain really is related to understanding what x does to y, and that is actually more than simply predicting y. Also this, please keep it in mind for now, but we're gonna touch upon that in this video here. A few issues that may stand in the way. So other factors could affect y. Okay, so there could be other factors other than x that determine our y. So how are we going to deal with those? Second, we want to understand how y varies with x. So we're going to have to somehow think about a functional relationship between y and x. Is it going to be a linear relationship between y and x, or is there going to be a non-linearity? Think of a production function. A production function has decreasing returns. So the first unit of an input will change output by more than a later unit of an input. So yeah, so how do we deal with that? And third, this notion comes back that we have seen in the first video of ceteris paribus. To what extent can we actually get at ceteris paribus effects to what extent can we isolate really the effect of of x on y, and related to that, to what extent can we actually get at a causal relationship and at estimating a causal relationship. Now, here's the first time in this presentation that we see the simple linear regression model written down. So it's going to be y is equal to beta naught plus beta 1 times x plus u. And on this slide here, you see some definitions of or some terminology that we're going to use. So in bold is always the terminology that is, in my view, the most common. Y is commonly referred to as the dependent variable. You can also say the explained variable or the regressand. X is the independent variable or explanatory variable or regressor. U captures unobserved factors affecting y. That is referred to as the error term or disturbance. Beta naught is the intercept or constant term. Beta 1 is the slope coefficient or parameter. So that's the coefficient on the x. And this one will actually capture ceteris paribus effects, because when you look at delta y and how it varies with delta x, then you see that delta y is equal to beta 1 times delta x, well, if delta u is equal to 0, right? And so you start from this relationship here, you change x, and the change in y is going to be the change in x times beta 1, provided that u is stable in the sense that delta u is equal to 0. This is what we're interested in, because delta x is going to be the change in the number of years of education, for instance. And yeah, the question is, how can we get at that when we don't observe u? Now, more specifically, let's think about this in terms of an example, or in the context of an example where the wage is equal to beta naught plus beta 1 times the number of years of education plus u. What's going to be important throughout, and certainly in the baseline case here that we're going to discuss first, is the so-called zero conditional mean assumption. And that's going to be important for learning about ceteris paribus effects beta 1 from a random sample that we're going to have access to. And the zero conditional mean assumption is that the expectation of the error term or disturbance for a given x is equal to the expectation of the error term unconditionally, so if we don't condition on x, and is equal to 0. Okay, this is a very rich statement already. So let's first of all look at this part in the middle. That's the expectation of the error term. Or let's look at this second equality. So the expectation of the error term equal to 0, that is called here an innocuous normalization. So what does that mean? It means that it's not really a strong assumption. We have written down a regression equation. That regression equation is y is beta naught plus beta 1 times x plus u. And what we can always do is we can always say, hey, we're going to assume that instead of 0 on average or in expectation, the u is equal to, say, 5, right? So if we would do that, then what we could simply do is we could, instead of beta naught, we could have a value that is smaller by 5, and we would have essentially exactly the same model. So we can always decrease the intercept by a certain amount and increase the error term in expectation by a certain amount, and that's not really going to change our model. What is important, however, is that we take a stance, that we fix one of the two. And the most common way to do that is to say that in expectation, the error term is equal to 0. The real assumption here is that the expectation of the error term does not depend on x, and that is hidden behind this first equality here. But once you know this, you can appreciate how it's written down here. So this says really that the expectation of u does not depend on x, because the expectation of u given x is equal to the expectation of u. What the expectation of u then is not really important, whether it's 0 or 5. This is just this innocuous normalization. But what is important, and this is the zero conditional mean assumption, is that the expectation of u given x is equal to the expectation of u. Now, in the wage example, in which, just for the moment, right, say that u is ability, okay? So what would that mean? It would mean that people who earn 5 euros more have 5 units more ability. This is just to fix ideas. What this would mean is that the expectation of ability, given that somebody goes 8 years to school, is equal to the expectation of ability when somebody goes to school for 16 years. So what this shows is that this is a really, really strong assumption that we would have to make here in this context, implausibly strong, right? Why is it implausibly strong? Well, because what is here in the conditioning set, this 8 and the 16, is actually a choice. And this choice is made in light of ability. So when somebody has a higher ability, is smarter, if you will, then that person will choose to go to school for longer, and then that immediately implies or means that this equality here does not hold anymore, because the expected ability of somebody who goes to school for 8 years would then be smaller than the expected ability for somebody who goes to school for 16 years. Now, under the zero conditional mean assumption, what we get is, and this comes from the linearity of the model, in the end of the day, of this equation that y is beta naught plus beta 1x plus u, we get that the expectation of y given x is the expectation of, we just plug in y here, which is beta naught plus beta 1x plus u given x. And then we have the expectation of a sum, the conditional expectation of a sum, which is the sum of the conditional expectations. So beta naught is a constant. So I get here the first element is equal to beta naught. Given x, the second element is beta 1x. Given x is beta 1x. So it's just this one here. And the third element is u, so it's the expectation of u given x, so that would be here the expectation of u given x, under conditional under the zero conditional mean assumption, this third element is going to be 0. So that means that the expectation of y, the dependent variable given x, is a linear function of x and is given by beta naught plus beta 1 x. Now, this allows me to draw this picture here. So what do we see? We see 3 values of x here on the horizontal axis. On the vertical axis, we see y, and the straight line here is this linear equation that we've seen on the previous slides. That will be the expectation of y given x, which is given because of our assumptions, because of the specification of the model, by beta naught plus beta 1 times x. So what else do we see here? We see these curvy lines. So what they're meant to represent are basically the distributions of y given x, because the model says y is beta naught plus beta 1x plus u. So for each value of u of x, u is going to have a distribution, and later we're actually going to assume that the distribution, well, for one case that the distribution is the same, and we're also going to discuss another case. But you know, this distribution here comes from the distribution of u given x. Okay, so that distribution of u given x could in principle be different for different values of x. However, what you do need is that for each value of x, that distribution has a mean of 0. That is our assumption. So it could be a different distribution for different values of x, but they all need to have a mean of 0. Now, the next step is to derive our OLS estimator. So what we want to do is to estimate beta naught and beta 1 using a random sample of data from our population. So the random sample would consist of pairs xi, yi, for observations I going from 1 up to n. Since we always have y is beta naught plus beta 1x plus u, we can just as well index everything by I, and then we have for observation I that yi is given by beta naught plus beta 1xi plus ui. And to provide you with an example, this is taken from the book. Here we have income and savings. So we have data on income and savings, and these dots here are my data points. And the straight line here would be the population relationship. So that's the expected savings given income, and that is beta naught plus beta 1 income that we wish to estimate, right? So all we get in our data are these data points, these dots, and we wish to estimate this relationship. This is the goal of the whole exercise. Now, towards doing that, let's derive the ordinary least squares estimates of beta naught and beta 1. Let me already tell you now that I will explain afterwards why this is called ordinary least squares. Because this is not obvious from the very beginning. But let's first look at what these estimates actually are, and later understand where this terminology comes from. Our starting point for deriving the ordinary least squares estimates are our assumptions. So we're actually going to start with the zero conditional mean assumption. First of all, if we state this assumption as the expectation of u given x is equal to 0, then it means that the expectation of u for each x is equal to 0, and therefore the expectation of u unconditionally is going to be equal to 0, and in that sense is implied. And the second thing that is implied is that the covariance between x and u, which is given by the expectation of x times u minus the expectation of u, which is 0, and therefore it's not even appearing here, is equal to 0. Now, at the same time, when we recall that y is beta naught plus beta 1x plus u, then of course we get that u is y minus beta naught minus beta 1x. And if we just substitute that in, so that expectation of u is equal to 0 into that expression here, then what we get is that the expectation of y minus beta naught minus beta 1x is equal to 0. If we take that covariance, which is the expectation of x times u is equal to 0, then we get that the expectation of x times y minus beta naught minus beta 1x is equal to 0. So why do we do that? Well, what we have now is we have two equations in two unknowns. Why is that? Because y is data and x is data. So the first equation has two unknowns, beta naught and beta 1, and the second equation has the exact same unknowns. The expectation of this term here has also the unknowns beta naught and beta 1. There's of course another thing that is unknown, which is the expectation itself. The trick here is, and this is a general approach in econometrics, and we're going to see this here only in this very specific context. It's called the method of moments. And what plays a role here is the so-called analog principle. So we don't observe expectations, right? So just think of data, right? You never observe an expectation of a y or an expectation of an x. What you will observe is an average of a y and an average of an x. Of course, the average is the sample counterpart of an expectation. So what we're going to do is we're going to say, hey, we're not going to have these expectations, but we're going to have averages. And the averages are actually observed in our sample. What the ordinary least squares estimates actually are, and I'm going to denote them here by beta naught hat and beta 1 hat, is that they satisfy the sample equivalent or analog of these two moment conditions. So these things are called the moment conditions, and they hold in the population. So for the population, we have these expectations. This is an expectation over draws from that population relationship, and they give me an average. So instead of looking at this expectation here and this expectation here, I'm just going to look at the sample counterpart, which is the average. So 1 over the number of observations times the sum over I from 1 to n of, and now I have the sample counterpart of this thing here, which is y minus beta naught minus beta 1x. So I'm going to have yi minus beta naught hat minus beta 1 hat xi, and that average is going to be equal to 0. And the second average looks almost the same, except that there's an additional xi appearing here. So it's the average of xi times yi minus beta naught hat minus beta 1 hat xi, and that's going to be equal to 0. Now, that's already good, Because when you look at these two averages here, this one here and this one here, I have two averages, which are basically two equations in two unknowns. So all I have to do is I have to solve for beta naught hat and beta 1 hat, and these are going to be my OLS estimates, which is great. Let's denote the average of a variable, for instance y, by y bar. So again, y bar is 1 over n, and then the sum I goes from 1 to n of yi. And now I'm going to plug in basically that yi is beta naught hat plus beta 1 hat xi. Then what I get is that the average y is going to be beta naught hat plus beta 1 hat x bar, which is the average x. What that means is that my intercept, my estimate of the intercept, my estimate of beta naught is going to be beta naught hat equal to the average y minus beta 1 hat times the average x. So that's the first result I'm already getting. But with this, I can't do much yet because it basically means, I first need to get my beta 1 hat. Otherwise, I cannot figure out what my beta naught hat is. But put differently, once I know my beta 1 hat, it's relatively easy to find out what my beta naught hat is going to be. Why is that? It's basically because of this zero mean assumption for the intercept, which translates into the average residual, which is yi minus beta naught hat minus beta 1 hat xi is equal to 0. And because of this average residual is equal to 0, I'm going to get my estimate of beta naught hat. So it's coming from that. Now, how do we get our estimate of beta 1 hat? In order to get that, I'm going to substitute actually my estimate beta naught hat, this functional form, which is given by this, into the second moment condition. And then what I get is that the average, which is 1 over n times the sum from 1 to n of xi times yi minus, and here I had beta naught hat. Well, here I'm going to substitute now in y bar minus beta 1 hat x bar, and then that stands now for this intercept term that I had before, which was beta naught hat, minus, and this is what I had before, beta 1 hat xi. So the average of that thing has to be equal to 0. That comes from my moment condition. So that I can just reorder things. But before we do that, what you see here is, of course, that the beta naught hat has disappeared, right? So I have now one equation in one unknown, which would be that beta 1 hat. So all I need to do is I need to solve for the beta 1 hat. How do I do that? I take this equation, which has on the right hand side 0, and what I do is I bring this term here to the left hand side, and then this term here is on the right hand side, and then all I need to do is to divide by that sum on the right hand side, and then the only thing left on the right hand side is beta 1 hat. Okay. Before I do that, let's briefly inspect where all these things come from. So on the left hand side of this equation, I now have the sum over xi times yi and xi minus xi times y bar. Where does this come from? So first of all, there is no 1 over n part anymore. This 1 over n part is not important because this this equation here has 1 over n times that sum equal to 0. I can just as well take away the 1 over n. I can just multiply both sides by n, then the 1 over n part goes away. So we don't need to bother about that anymore. So the only thing left is that sum. And then I bring some things to the other side of this equation. So what stays is the xi times yi part and the xi times minus y bar part. So this is all this here. And what goes to the other side is everything that is multiplied with beta 1 hat. So that would be xi times minus and then again minus beta 1 hat x bar. So therefore I have here beta 1 hat xi minus x bar. And then I have the other one left is xi times minus beta 1 hat xi. And that would be the xi times xi part here, which is pre-multiplied by beta 1 hat. So then I have this equation here, and in order to solve for beta 1 hat, all I have to do is to divide by this sum here, and I'm allowed to do that when that sum is not equal to 0. So provided that this sum, which can be written actually as xi minus x bar squared, is greater than 0, what we get is this result here. So what is, before we get to this result, what is happening here? This is exactly the formula you know from statistics when it came to estimating a variance, right? So that's the formula for a sample variance. So you can write that as 1 over n times the sum of xi minus x bar times xi minus x bar, but you can also just take the minus x bar away or leave it away for one of the two expressions. So you can always write it like this, right? So this is the formula you have seen in your statistics class. Now, this is what we get here. So we divide by this, and then we get that beta 1 hat is the ratio of these two sums. And as I just said, we can always write it in terms of an xi or an xi minus x bar. It doesn't matter. That is coming from the fact that the sum over this thing here is actually 0, right? The sum of yi minus y bar is equal to 0, and therefore I can always add and subtract a constant term here, which would be that x bar. Good. What do we get when we do all this? And this is the important part here. I'm getting that beta 1 hat is, now if I add a 1 over n here and I add a 1 over n here, I can always do that. Then I have here actually the covariance between x and y divided by the variance of x, or to be very specific, it's an estimate of the covariance between x and y divided by an estimate of the variance of x. Let's briefly talk about this condition. Let me go back here, right? We needed, in order to divide by this sum here, we needed that the variance of x is greater than 0. Let's just think for the moment of the case where the variance of x is not greater than 0. It basically gives us a plot like this one here. So if you would have a scatter plot of the wage against education. So when the sample variance of education, which would be my x, is 0, it means there is no variation in education in my sample. What is then the case is that I can never really learn from my data about the relationship between wages and education, because I have no variation in education. So it's a very, very natural condition that we have used here. So we shouldn't worry about it too much. So when we don't have variation in education, it's basically a non-starter. We don't even have to bother to obtain our estimates, because it's not going to be possible. Now, let's talk about the terminology. So I said before that we will first get to our estimates and then we talk about the terminology. This estimator is called the ordinary least squares estimator, because we get to the exact same result, which again is that our estimate of the slope coefficient is the sample covariance between x and y divided by the sample variance of x, and our estimate of the intercept is the average y minus the average x times our estimate of the slope. We get to the exact same estimates when we start from a criterion function and then minimize that criterion function. What is that criterion function? The criterion function is the sum of the squared residuals. What are the residuals? They're here denoted by ui hat, and they're squared then. What is the residual? The residual would be the difference between the actual value, yi, and the predicted value, yi hat. How do I get this prediction? The prediction is simply beta naught hat plus beta 1 hat xi. This is with a minus here, so therefore I'm getting minus beta naught hat minus beta 1 hat xi. So I'm just substituting that in. This is my sum of squared residuals, and these sample moment conditions that were the starting point for my earlier derivations are simply the first order conditions for the minimization problem. Minimize that sum of squared residuals by choosing beta naught hat and beta 1 hat. So there's a very natural explanation for that name, but we didn't even have to write down that goal function. We simply started from these moment conditions instead, which are that the expectation of u is equal to 0 and that the covariance between u and x is equal to 0, and both came from this zero conditional mean assumption that the expectation of u given x is equal to 0, and we simply started from these two moment conditions and worked with the sample analog, which basically takes them and replaces expectations by averages. So two ways to get started, both lead to the same result, which is elegant and beautiful and nice, and I hope you can also appreciate that. Let's draw a picture to build that intuition and terminology a little bit more. Not build, but to memorize it or to learn it. So here I have my regression line. So y hat is equal to beta naught hat plus beta 1 hat x. So I can now draw this picture. Actually, this is known to me because I have these two beta hats and I have my x's in my data. So I can plot this line for any x actually, and then I have my data points, which are these dots, and then the difference between a data point and the regression line for the same xi is always going to be my residual, and that is the fitted value, the point on the line. And here is again my sample regression function, or a fitted value would then be yi hat is equal to beta naught hat plus beta 1 hat times xi. Here, what this picture tells you is for the example data from the book on CEO salaries, and we've seen that picture before. I told you that there is a relationship. So I'm actually not sure whether I showed you exactly this picture before, but this is the return on equity. The true underlying relationship is this one here. The expectation of CEO salary given the return on equity of that firm would be beta naught plus beta 1 return on equity. And with data, what we're going to estimate is this solid line here, which differs in general from the population line. So that's the fitted value of the salary, and here we get these coefficients, and it looks like this. Okay, so what this picture tells you is there is a difference between the true underlying relationship and our estimates. Why is that? Because we have only a few data points, right? We're not going to get it exactly right. We're going to get an estimate of this line, but hopefully that estimate will not be too far away. And importantly, what we can do is we can use data to learn how accurate our estimates are. And this is what we're going to work towards now. Before we get there, these are examples from two other data sets. So if you regress wages on education, what you find is this relationship here. And if you regress voting outcomes on campaign expenditures, you get this relationship here. So you always get an estimate of the intercept, you always get an estimate of the slope, and with this you can get the fitted values for any value of education or campaign expenditures, this is easy to do, and obviously this is with a computer, you get these coefficient estimates in no time. So let's think about properties of OLS on any sample of data. Towards that, let's quickly go back to the example of CEO salary and returns on equity. So what you see here is a table with observation numbers, return on equity, salary, predicted salary, and U hat. And U hat would be the residual. So that is UI hat from a few slides ago. And we do know that on average the UI hat is going to be equal to 0. But let's discuss these properties one by one. So first of all, we had those sample moment conditions. We had two equations and two unknowns. And what this means is that these two equations are going to hold exactly, right? So one was that the average or the sum of the U hats is equal to 0, which is the same as saying that the average U hat is equal to 0. And the other one is that the sample covariance between UI hat and xi is equal to 0, which means also that the sum of the xi UI hats is equal to 0. Now, I already talked about this property that the average y is going to be equal to beta naught plus beta 1 beta naught hat plus beta 1 hat x bar, which is the average x, and this comes basically from the first bullet point, as we have already seen on that previous slide. And what it means is that the point given by the average x and the average y is actually going to lie on our regression line. So these are things that will always hold, right? So each time you get a sample with data, so just make the thought experiment of getting data, estimating that relationship, getting new data, estimating again that relationship. Every single time your regression line is going to go through the point x bar, y bar, so average x, average y, and each time by construction you get that these two moment conditions hold. At the same time, each time you will get different beta naught hats and beta 1 hats. That's also important to realize. Now, the next thing I want to discuss is something that's related to interpreting the results and to talking about the goodness of fit. When you have the data, then we're going to have a yi, and for our given estimates, beta naught hat and beta 1 hat, we're going to have a yi hat and a ui hat. And we can write down always by definition that yi is equal to yi hat plus ui hat. And if I then take the average, because the ui hat on average is going to be equal to 0, then I'm going to have that the average y hat is going to be equal to the average y in my data. At the same time, I'm going to have that the covariance between the fitted residuals and the predicted value of y minus y hat is equal to 0. And from all this, what I can show is that the following relationship holds, and I'm going to define these quantities in a bit. It says that the total sum of squares is equal to the explained sum of squares plus the residual sum of squares. So what is that? The total sum of squares would be basically n times the variance of y. The explained sum of squares is n times the variance of y hat, and the residual sum of squares is n times the variance of the residuals. And that will always hold by construction. So I can always write it down like this. So it's basically saying that I can decompose the total variation in my data in the y into a part that is explained by variation in x through that model that I'm estimating here with these two coefficients, and variation in residuals that is not explained. Now, taking this as a starting point, what you can do is you can develop or write down a measure that is useful because it's unit free. So it's called the R-squared measure. Sometimes it's also called the coefficient of determination, but most people know it for sure as the R-squared, and it would be equal to the explained sum of squares. So by definition, it's the explained sum of squares divided by the total sum of squares, and by means of the equation on the previous slide, since the total sum of squares is the explained plus the residual sum of squares, we're going to get that this is equal to the explained sum of squares is the total minus the residual. So it's this ratio here is total divided by total minus residual divided by total. So 1 minus residual sum of square divided by total sum of squares. And this will measure the fraction in the sample, variation in y, that is explained by x. So explained fraction divided by total fraction. By definition and by construction, this measure is going to be between 0 and 1, which is set here. And one thing that's really important to realize is that a low R-squared measure is actually common in cross-sectional economic analysis. So if somebody tells you that this measure is 2%, you should not get worried. So it could still be that the coefficient that you're interested in, this beta 1 hat, is a very good estimate of your ceteris paribus relationship. All it means is that many things that could have an impact on your y are not in your model, right? But that's okay, because you're not in the business of explaining as much of the variation as possible. You're in the business of understanding the relationship between one particular x and the y. So in that sense, that is perfectly fine. Now, let's next talk about units of measurement and functional form. Let's go back to this wage and education example. And let's ask the question, what actually happens if we rescale the wage? So suppose we would rescale the wage from hourly to daily. Think about it. We have a linear relationship. Y is beta naught plus beta 1x plus u. And what we do now is we basically change the unit of measurement on the left-hand side. So from hourly to daily. So let's say somebody works instead of works 8 hours a day. So then what that would do is it would basically take that whole equation and multiply the left-hand side by 8. So what that means is that the intercept will be multiplied by 8, and at the same time the coefficient on education will be multiplied by 8. What happens to the intercept? Well, it's also multiplied by 8. But you can already see from this that if you just rescale the wage, all it will do is it will take your estimates from before and will rescale them 1-to-1. What happens if we rescale instead education from years to months? Well, something similar happens. One unit change in education was before it was a year, right? And that year had a certain effect. Let's call this beta 1, and it was estimated as beta 1 hat. Now, if we rescale education, then a unit change in education will not be a year anymore, but will be a month. What we will get is the effect of that 1 month of changing education, and that will be lower. So it will be actually 1/12 of the earlier effect. So what that means is that the coefficient on education will be the exact same number as before in terms of the population quantity and the estimate, but then divided by 12. What is more interesting than just rescaling things is to also think about the functional form. So there are two very popular transformations, and I'm gonna just introduce them to you very briefly here. We're gonna talk about them more in class. If we would, instead of just writing down wage is equal to beta naught plus beta 1 education plus u, if we would write down the log of wage is equal to beta naught plus beta 1 education plus u, then what we actually get is that the coefficient here on education times 100 will not measure an absolute effect of education on wages, but it will estimate a percentage change in wages given one additional year of schooling. And this log specification, and therefore I want to talk about that more in class, is actually a very useful specification in practice. It often works extremely well. Another specification that is often used is a so-called log-log model. And when you have a log-log model, then what you would have is that you would regress the log of the wage on the log of education. Okay? And what you can then show is that beta 1 is an elasticity. What that means is beta 1 is the percentage change in wages if you change education by 1%. This is actually, in the context of education, this is not so often used, but in the context of price effects. So it would be the percentage change in demand if you change prices by 1%. So this is so-called price elasticity, and this is a very important quantity in the context of demand analysis. Importantly, we're still having a linear model here. We're still having a linear model in the parameters. So when you look at this wage equation here, you see that it's still linear in the betas. Okay, and that is important, and that means that we can still run OLS, right? We just have a transformed variable here on the left-hand side, but we will still do exactly the same as before. Let me just show you the underlying equation. So if you start from this equation here, that the wage is the exponential function applied to beta naught plus beta 1 education, and actually if you would add a disturbance plus u also in the as the argument of this exponential function, but we can also do it without, just to illustrate, and we take the log, then we get exactly from this that the log of the wage is the log of the exponential function, so that will just cancel. So it's going to be beta naught plus beta 1 education. So it's going to look like this. So when beta 1 is positive, then the underlying relationship will look like this. And that has to be because a 1 unit increase in education will have a certain percentage effect, and the higher education is, the higher the baseline is. So it has to be a convex function. The next thing we want to do is to look at expected values and variances of the OLS estimators. These are statistical properties, and the right way to think about this is that we're going to get a sample for our data, and then we're going to get estimates for that sample, and then we're going to get another sample and we get new estimates. We get a third sample, we again get estimates. The question then becomes, what is the expected value across samples of our estimates, and what is the variance? And the expected value is going to tell us how good we are on average, and the variance is going to tell us how precisely we're going to be able to estimate our parameters when we have one single random sample from the population. Now, that is, we're going to look at the distribution of the OLS estimators beta naught hat and beta 1 hat over repeated random samples from the population. let's look at some assumptions we're going to need for that. So the first assumption, or let's formalize this. The first assumption we're going to formally make is that of linearity in the parameters. And that is simply our functional form assumption that we have already seen. Y is beta naught plus beta 1x plus u. So this assumption is going to be SLR1, simple linear regression model number 1. The second assumption is random sampling. So that's basically saying we have data from a cross-section of we have cross-sectional data. So we have a random sample xi, yi, always pairs. I runs from 1 to n, and they follow the population model in assumption number 1, that linear model. These two assumptions, SLR1 and SLR2, imply that for each observation yi is beta naught plus beta 1 xi plus ui. We've seen that before, that's already that's also in this figure here. This figure plots y against x. Each dot in this figure is an observation, it is a particular combination of xi and yi, and what we do know is that yi is the systematic part, beta naught plus beta 1x. That's the population regression function, for which we can also write down that the expectation, which is that the expectation of y given x is beta naught plus beta 1x. And then we have this observation, for instance, this one here. So we know that for this observation, that this is going to be the population regression function for that particular value of x, which is xi, plus ui. So ui is the error term for that observation I. Now, towards studying statistical properties, let's make some more assumptions. SLR3 is called sample variation in the explanatory variable, and it says that the sample values x1, 2, up to xn of the explanatory variables are not all the same. And we have seen that before when we wrote down, or when we derived the formula for the OLS estimator of the slope coefficient beta 1 hat. The next assumption, SLR4, is the one of zero conditional mean. And we've seen that before as well. It says that the expectation of u given x is equal to 0. So we have discussed before that two things are important here. One thing is that for each value of x, the expectation of u is the same. So it does not depend on x. And you can see this because essentially here on the right hand side, x is not appearing. And the second part is that on average, the u is going to be 0. And of course, it's 0 on average, but also by means of that first part of the assumption, for every value of x, it's going to be equal to 0. Given these four assumptions, we can get to the statement in theorem 2.1, which is unbiasedness of OLS. And the statement is that in expectation across random samples or over random samples, the estimator beta naught hat is equal to beta naught, and the estimator beta 1 hat is equal to beta 1. So loosely speaking, on average, we're estimating the right thing on average across random samples that we get in our data. Now, let's look at an example. So for the wage and education example, what we have is that the fitted line, the regression line that we're going to be able to estimate, wage hat is going to be equal to minus 0.9 plus 0.54 times education. Okay. The question is, how can we interpret these numbers under the four assumptions that we have just seen? So first of all, usually we won't really interpret the intercept term, but if you really want to, you can say, for instance, if somebody has no education at all, then literally this would be saying that the wage is negative. Obviously, everybody has some education, this already tells you that it's a little bit iffy to interpret the intercept. What one does normally interpret is the slope coefficient. So here we have one slope coefficient because we have a bivariate model. Bivariate means 1x. That slope coefficient is 0.54. So let's say wages are measured in US dollars because this is US data set. Then it means that one additional year of education causes wages to increase by 0.54 US dollars. I use the word causes, so you can also say the effect of education on wages is of one more year of education on wages is going to be 0.54 dollars. Now, this interpretation is done under assumption SLR4 in particular, but SLR4 might fail, and the question then is, how does this affect the interpretation? Well, we should then not interpret this as a causal effect anymore. However, what we can still say is that wages for those who have more education who have one more year of education are higher by 0.54 US dollars. So what we're doing then is we're not going to talk about effects. We're going to compare basically two different people, or two different groups of people, right? So we're gonna say, okay, let's just compare wages for those who have 16 years of education to wages of those who have 15 years of education. There's a difference in the average of the wage that we're going to see in our data. However, we should not interpret this difference as an effect of one more year of education, because people who have 16 years of education might be very different from people who have 15 years of education, or might be somewhat different. So one should not attribute all the difference in the average wage to that one extra year of education. Now, the third question is, under these four assumptions, how close can we expect 0.54 to be to beta 1? So 0.54 is beta 1 hat. So far we can't say much about this. What we can say is that if we basically get many random samples, each time estimate beta 1, then on average we're going to be right. But of course, that's not going to help us here, because 0.54 is just one single instance where we calculate this slope coefficient. So what we're going to need is, in any case, an additional assumption for deriving the variances of the OLS estimators. And the simplest possible, most standard assumption is the one of so-called homoscedasticity. And that assumption is on the variance of U. So let's denote that variance by sigma square. And the assumption then is that the variance of u given x is equal to sigma square. What this is saying is that the variance of u does actually not depend on x. And that is exactly the assumption of homoscedasticity. So there is no relationship between x and the variance of u. Now, if you take SLR4 and SLR5 together, then it turns out that you can say that taken together, they're equivalent to saying that the expectation of y given x is beta naught plus beta 1x. We've seen that before. That's essentially, that is the population regression function. But at the same time, I have that the variance of y given x is a sigma square. So notice that up here I had the variance of u given x equal to sigma square. But of course, when I hold x constant, then and I basically look at the equation y is beta naught plus beta 1x plus u, and I look at the variance of y given x, it's going to be the variance of, well, beta naught is not going to vary, beta 1x is not going to vary if I hold x constant, so the only thing that can actually vary is u, so the variance of y given x is actually the variance of u given x under homoscedasticity. Okay, and that homoscedasticity comes back here. Good. Yeah, one way to illustrate this is to draw a picture like this one here. What you have here is here you have x, here you have y, and here you have always the distribution, actually, the density of y. So here you see that that distribution here has the same variance than this distribution here, and has the same variance than this distribution here. So by means of the fourth assumption, the mean has to lie on that line here, of course. The shape of the distribution in principle does not have to be exactly the same, but what needs to be the same is the variance of u given x, or equivalently, as we just saw, the variance of y given x. Now, what's a counterexample to all this? So think of the relationship between wages and education. So here we have education, here we have wages, here we have again this density, and then one could think that, you know, for low levels of education, the mean of wages is going to be lower, and it's going to be higher for higher levels, but also the variance is going to be lower than it is for high levels of education. So you can think of this as a counterexample, and actually we're going to come back to this later in the course, and we're going to see what we can do about this. For now, this is good to keep in mind. Good. Now we have all that we need in order to say something about the variances of the OLS estimators across random samples. We have already made a statement in theorem 2.1 about the means of these OLS estimators, and now we're going to talk about the variances, and that's going to tell us how precisely we can, how sure we can be that we're close to the true values. And here I'm only giving you the results. So under the 5 assumptions that we have seen, SLR1 up to SLR5, and implicitly conditional on the particular draw of x's that we get, what we get for the variances are these formulas here. So instead of telling you how exactly we're deriving them, I can tell you, in principle, what you do is you take the formula of beta 1 hat and beta naught hat, and then you just look at the variance of that thing, conditional on x. So and that involves the variance of u that then expresses itself in those formulas here. But I'm not gonna show this to you here in detail. Rather, I'd like to interpret these two formulas. So what you can see here, first when you look at the slope coefficient, what we can see here is that variance is going to be bigger the bigger sigma square. So that makes sense because the more sigma, so the bigger sigma square, the more variance my u is going to have. So the more noise I have in my data, the more unexplained variation is there. That makes it hard for me to learn about the systematic variation of y with x. So it does make sense that this depends positively on sigma square. At the same time, I see that variation in x appears in the denominator. So that also makes sense. So the more variation I have in my x's, the better I can learn about my parameter of interest, which here is beta 1, right? So before we have seen that case in which we only had no variation basically in the x. So that was the example where we only have one level of education for everybody in our sample. And if this is the case, then we can't learn anything, as we have already seen. Here what we see is that the more variation there is in x, the more we can learn. So what we have here in the denominator is the total sum of squares for x, which is here indicated by this little subscript x. What you can also see is a dependence on n, the sample size. So when you look at this formula here, you see that as the sample grows, the denominator is going to grow because any element that is added is squared. So this sum only has positive elements. So when n increases, then the denominator is going to grow, and this makes perfect sense. So if I have many observations, then in the limit I'm going to be able to learn, very well what my value of beta 1 is from my sample. Now, for the variance of beta naught hat, we have a similar formula. So again, we have a positive dependence on sigma square. We have a positive dependence on the sample size in the denominator, and in addition we have this extra quantity here, which is the average of xi square. Okay, so that tells you that here things are a little bit less intuitive, and that comes from, here this is the this is the intercept, right? The estimate of the intercept. It will depend on these x's, because in the end of the day, recall how we compute the intercept. We basically take the average y, and we subtract from this our estimate of beta 1 hat times the average x, and that's going to give us our intercept. So the estimation error in the beta 1 hat is going to also appear here in the estimate of beta naught hat. So at least I personally find this second formula a little bit less intuitive for that reason. Now, how much further can we go? Well, first of all, we can actually try to estimate these these two quantities. So all we need for this is to estimate sigma square. And it turns out that this is not too hard to do. So sigma square is the variance of u. And what we can do in order to estimate the variance of u is we can take the variance of the residuals. That's the main idea. On average, the residuals are going to be 0. So a good estimate can already be obtained by just squaring the residuals and adding them up and then dividing by the sample size. So here you see that I'm not dividing by n, but I'm dividing by n minus 2. And that has to do with the reason for this is that we do here a degree of freedom correction. So you've seen that before in statistics, that when you estimate a variance, you might want to divide by n minus 1 in that particular case. Here we want to divide by n minus 2 because we're actually estimating 2 parameters. In statistics, when we divided by n minus 1, we basically only estimated 1 parameter, which was the mean of that variable when we estimated a variance. That's a detail. It's not an essential difference between the approaches. So it's just this additional degree of freedom we lose because we're basically estimating 2 parameters. And then once we substitute sigma square hat, this estimate, for sigma square in the appropriate expressions, we get what is called the standard error of the regression. So that is the sigma hat, if you like. So that's the square root of sigma square hat, and an estimate of the variance of beta 1 hat, and from this we get the standard error, which is just the square root, etc., etc. And we can use this to do testing, right? As an example, you can use the data set and you get these quantities basically when you run a regression, and you can calculate them, and they tell you something about the precision of your estimates. Now, this brings us to theorem 2.3, which is a formalization of this whole procedure. And the title of theorem 2.3 is unbiased estimation of sigma square. And the statement is that under assumption SLR1 up to SLR5, in expectation, we're going to do the right thing by using sigma square hat as an estimate of what we're interested in, because in expectation sigma square hat is going to be equal to sigma square for a given sample size, and this is of course great. Finally, what we've had is the bivariate model up to now. So this was the model beta naught plus beta 1x plus u. And this model had an intercept, right? So for x is equal to 0, y in expectation had a value that was not 0. But sometimes, one can say, I know that it has to be 0 for whatever reason. So we can also think about running OLS without an intercept. That would be the alternative regression line y tilde, and that would be beta 1 tilde x. And then we're basically doing the same thing, but we're setting beta not equal to 0. And then we're repeating the whole exercise. We're going to minimize, if we think of it in terms of a goal function, the sum of squared residuals. So it would be yi minus beta 1 tilde xi square, which gives the moment of first order conditions that look like this. Exactly, it gives one first order condition because we only have one parameter. it looks like this, which is exactly corresponding to what we had, which was the second one before, because the first one is now gone. So what we're going to get is that beta 1 tilde hat, beta 1 tilde, which is now our estimate, beta 1 tilde hat should be here, is given by, again, the covariance in the end of the day between x and y divided by the variance of x, but it's basically here now xi yi summed over n divided by xi squared summed over n. If this assumption is correct, so if x bar is equal to 0, then these two are going to be exactly the same. But if not, so if actually beta naught is not equal to 0, then beta 1 tilde is going to be biased. This is to say, in principle, you can simplify the whole argument and do the whole thing without an intercept, but you run the risk of getting a biased estimate of the slope if you're wrong. There's no real cost to including an intercept, which is why normally in applied work you would do that. Good, and this actually is the last thing I wanted to show you related to the bivariate or simple regression model. I hope this was clear, and with this, all the best.